60% of the body's weight consists of fluid. Of that, 2/3 is intracellular fluid and 1/3 is extracellular fluid. The extracellular fluid consists 25% of plasma and the other 75% is interstitial fluid. If any of that is hard to keep track of, just refer to this diagram right here, which is based on total body weight. The fluids are separated by a semi-permeable membrane. Osmosis is the net movement of water across a semi-permeable membrane from areas of high concentration to areas of low concentration. Tonicity refers to the solute concentration and the net movement of water. Here we have two environments separated by a semi-permeable membrane. On the left we have an area of low concentration and on the right we have an area of high concentration. Low solute concentration equals low tonicity, whereas high concentration equals high tonicity. To demonstrate tonicity, let's place some red blood cells in a beaker of water. Here the solute concentration is greater inside the cells than in the surrounding water. In other words, the content of the cells are hypertonic in relation to the hypotonic concentration of the water. Because there is a higher concentration inside the cell, then in order to reach equilibrium, the water will move inside the cell, causing it to swell and sometimes burst. If the red blood cells were placed in a solution that was higher in concentration, then the concentration would be hypertonic, whereas the red blood cells would be hypotonic. Both solutions would like to be equal in solute concentration. Therefore, the water would move from inside the cells to the surrounding solution. Tonicity and osmolarity often get confused. As a reference point, tonicity deals with concentration, volume, and the environments of a cell if allowed to come to equilibrium. On the other hand, osmolarity looks at the sum of the molarities of the dissolved particles of a solution. For example, in an aqueous environment, NaCl would dissolve into two separate molecules, Na plus and Cl minus, the ionic forms. If the solute particles can enter the cell, we call them penetrating solutes. We call particles that cannot cross the membrane non-penetrating solutes. Tonicity depends on the concentration of non-penetrating solutes only. Sodium chloride is probably the most common non-penetrating solute. In this example, we have 3 non-penetrating solutes in the cell and 3 non-penetrating solutes in the solution. For osmolarity, we're looking at the solutes. So because there's 3 non-penetrating solutes in each, we can conclude that the solution is isoosmotic. When looking at tonicity, what helps me is looking at where the concentration of water is going. In this example, there are 3 non-penetrating solutes on each side, so there's going to be no net movement of water. In this example, the solution has 2 non-penetrating solutes, whereas the cell has 3. Therefore, we can conclude that the solution is hypoosmotic. With tonicity, again, we are looking at where the movement of water would be. Because there is a higher concentration inside the cell than outside, water would move inside the cell to create an equilibrium. This would cause the cell to swell. And if the cell swells, then the solution is hypotonic. For osmolarity in this example, we look at the solution to see how it has one more non-penetrating solute than the cell. So because it has more, we can conclude it is hyperosmotic. For tonicity, we look at the direction of water flow. Because there is a higher concentration in the solution, water would move from inside the cell into the solution, causing the cell to shrink, and for the solution to be hypertonic. In this example, I have introduced penetrating solutes. For osmolarity, it doesn't matter whether it's penetrating or non-penetrating. Now for tonicity, we need to note that the water will move to the non-penetrating side, causing the cell to swell and for the solution to be hypotonic. In diffusion, the molecules may freely move through the membrane through simple diffusion, and with certain channel proteins such as aquaporins, water may move through in a process called facilitated diffusion. In order for larger molecules such as glucose, bacteria, or other proteins, the cell requires energy such as ATP to move it into the cell. Here we have primary active transport and secondary active transport. The electrochemical gradients set up by primary active transport store energy, which can be released as ions that move back down with the concentration gradient. Secondary active transport, however, uses energy stored in these gradients to move against their concentration gradient. There are a few ways non-penetrating solutes may move across the membrane. As I noted before, certain channels such as aquaporins can help water move through. Ion channels may be specific for one ion, or may allow ions of similar size and charge to pass. For example, sodium and potassium ion channels. Next we have open channels. Open channels or leak channels spend most of their time with their gates open, allowing ions to move back and forth across the membrane without regulation. These gates may occasionally flicker closed. Lastly, we have gated channels. Gated channels spend most of their time closed, but when they open, they allow ions to pass through them. Ligand-gated or chemically gated channels are also called ionotropic receptors because they allow ions. Mechanically gated channels respond to physical forces such as an increase in temperature or pressure that puts tension on the membrane and pops it open. Voltage gated channels open and close when the electrical state of the cell changes.